So now some examples of the integral acting as an accumulator. We're not quite ready to talk about area and volume, so we're going to stick with kind of these ideas of we're accumulating a rate of change to find the net change. So for example, from 1970 to 1980, the rate of potato consumption in the US is given by this function C of t, which is equal to 2.2 plus 1.1 t million bushels per year, with t being years since the start of 1970. So in other words, if I'm thinking that the start of 1970, that would mean t is 0. How many bushels of potatoes were consumed from the beginning of 1972 to the end of 1973? Well, when I see that I'm given a rate, but they're asking me how many, that's a clue that I need to accumulate the rate. So accumulating the rate means I'm taking the integral of the rate. They called it C of t, so I'm just going to write C of t. I could also have written the actual function, 2.2 plus 1.1 to the t dt. In terms of the AP exam, writing either of those is correct because they defined what C of t was. But then I need bounds for this. Well, my bounds are not going to be from 1972 to 1973 because t equals 0 is the start of 1970. So if t equals 0 is the start of 1970, that means t equals 1 is the start of 1971, t equals 2 is the start of 1972. So, whoops, my lower bound is going to be 2. For my upper bound, well, the end of 1973 is the beginning of 1974. So I could really have phrased this as it's from the beginning of 72 to the beginning of 74. So my upper bound is 4. Now, this is an integral that can be done by hand, but in the interest of time, and because this video is not focusing on the actual process of integrating, but how we use integrals, I'm using my calculator for it. And because it's been a while, remember, when we have decimals for answers, we round to 3 decimal places at the end of the problem. So with either of these, they result in 7.066 as an answer. But I'm asked how many bushels. This is not 7.066 bushels. I have to look at my units. C of t was millions of bushels per year. Well, when I integrated C of t, unit-wise, I took the millions of bushels per year, that is the C of t, times the units of dt, which are years. Well, millions of bushels per year times year leaves me with millions of bushels. And there is my answer. If I tweak this a little bit, and instead of saying I want to find the net change of something, I want to find a final value. So if we have a pizza heated to a temperature of 350 degrees Fahrenheit, taken out of an oven, and placed in a 75-degree room. From algebra class, you may remember doing the Newton's Law of Cooling lab. This is basically the idea of it. The temperature of a pizza is changing at a rate of negative 110 e to the negative 0.4 t degrees Fahrenheit per minute. To the nearest degree, what is the temperature of the pizza at 5 minutes? So again, things that I'm seeing as clues. I'm given a rate, but I'm asked to find a temperature. So that clues me into I need to accumulate my rate. I'm going to say that for shorthand shape, I'm going to call this capital T of little t. So capital T for temperature, little t for time. So because I've named it, I can use that in my integral instead of rewriting it. So I want to accumulate the rate. My bounds, well, when it's taken out of, it doesn't start cooling off until it's taken out of the oven. So as soon as I take it out of the oven, the time is 0. and I'm told 5 minutes, so up until 5. But I have to think about what this tells me. This is going to tell me the change in temperature because I'm accumulating a rate of change. It gives me the amount of change. And actually, even if I only find just that value by itself is a negative number, negative 237.783 degrees Fahrenheit. And I should be able to tell that doesn't make sense as an answer for a pizza taken out of an oven for 5 minutes to go from 350 degrees Fahrenheit to a temperature of negative 237.783 degrees Fahrenheit. That's just ridiculous in a 75-degree room. So what I need to do is I need to add on the temperature that it started at, which is 350 degrees. And that should give me the temperature after 5 minutes of sitting in the room. If you notice, this is now the FTC with a twist. My ending is equal to my starting plus the integral of the rate of change. For those of you who want to know what this is simplified, that is because we're actually told to go to the nearest degree. So that's 112 degrees Fahrenheit. It does tell me that it's different from rounding to the 3 decimals, so I do have to follow the directions if they tell me go to the nearest degree. And this is my answer. For example 3, we could do this from data. So this is the way like pipelines, like an oil pipeline or a water pipeline, how they actually measure how much liquid is passing through the pipeline. They don't continuously just measure the amount. What they do is they have sensors at different places in the pipeline that measure the rate of change, in this case we'll say water, as it passes by that point. It does, because of computers, we can measure it more accurately and more often because the computers take the measurements and the computers do all of this work for us. But this is the idea of how we measure. So we have a water pump operating at a varying rate shown in the table, and we're going to use a Riemann sum to estimate how many gallons were pumped during the 15 minutes. Again, what I'm noticing is they tell me about the rate, but they ask me how many gallons. So that tells me I want to do an integral of the rate. And they're saying for the first 15 minutes, so from 0 to 15. I don't have an explicit equation for the rate. I just have a table of data, so they do tell me to estimate. And remember, on the AP exam, a Riemann sum is right RAM. So my first rectangle is from 0 to 5, so that's a width of 5. The right-hand side, the 58, is its height. For my next rectangle, from 5 to 10, that's a width of 5. The height is the right side, the 60. For the third rectangle, that's from 10 to 15, so a width of 5, and the right side gives a height of 65. And our rate was in gallons per minute, and dt is time, which is in minutes. So my units are gallons. And again, if you're being asked to do a Riemann sum, don't simplify it. Leave it unsimplified. It saves time and it minimizes the chance of a mistake. But again, we were told about rate and asked about how much. In this case, how much was the change, not the rate of change. So we accumulate the rate of change. If we go to a motion example, we have a particle moving along the x-axis with velocity given by that equation for t from 0 to 5, and it starts at a position of 9. So the first thing we're asked is what's the particle's displacement from 0 to 5? Motion's a little bit tougher to notice, but velocity is the derivative of displacement, or in other words, if we change the name of derivative to instantaneous rate of change, I'm told the rate of change, but asked how much change, because displacement is how much is the change in position. So I'm given the rate of change and asked for the amount of change. So that means I need to accumulate the rate. So I can accumulate this rate. They tell me it's from 0 to 5, so that's my bounds. Again, this is one you could do by hand, and I recommend practicing that on a regular basis. But in the interest of time on this video, and because it's not the purpose of the video, I'm just using my calculator, and that is 35. I was not given units, so I'm not going to write any units. But then part B says, what's the particle's position at t equals 5? So it's not how much has the position changed, but where is it? In other words, where is it ending? So I know it starts at 9. I need to know where it ends. So this is the idea of the FTC with a twist. I want to know its ending, so I take its starting and add on how much it changed. Well, we're told it starts at 9. We found in part A that how much its position changed is 35. So we get a final position at 44. Distance is a little bit tougher. What you have to remember is distance can never be negative, whereas displacement could. So the way we think about it is velocity is the derivative of displacement, or displacement comes from accumulating velocity. And that's okay because velocities are allowed to be negative, displacement's allowed to be negative. For distance, we need to accumulate something, a rate of change that can't be negative. So what we want to do is we want to accumulate speed. So remember, speed is just the absolute value of velocity from 0 to 5. This typically will be a calculator required question. If it's not, it's one where they give you the graph and its basic geometric shapes for the graph. But if I accumulate speed, that will give me the distance of 42.587.